Good. So, the one way to think about the fundamental theorem of calculus, which just, again, makes it really, really obvious what's going on, is to just kind of just draw sort of a picture of an accumulator function. Well, what is an accumulator function? We start somewhere, who cares where, let's call it like little a or whatever, and then we have some function, right? And let's call the function f. And what we're doing is we are thinking of all the area accumulated so far as like its own function. Let's call this function, big B for bunch of area we got. Okay, so good. So is everyone feeling that as x moves to the right, like we just are getting more and more, and the b function is like changing, yeah? Okay, well, what we are asking for is simply, what is the derivative of the b function? And what does it even mean to take the derivative of the function? Well, it's asking for the rate at which this function is changing. And so what we're really asking is, dude, given a tiny little increase in x, what is the increase in the b of x? Or maybe we just want to even go more casual and be like, yo, what's the change in the b function given a tiny change in x? That's the question we're really asking now, right? Well, in order to answer that question, let me just make x a tiny bit bigger. So now I'll go over here in blue and just call this like x plus delta x. And, well, how much do I get in x plus delta x? I get this tiny little, in that infinitely small amount of new x, I get this tiny rectangle. And what is the area of this rectangle? Basically,
delta x.
It's a rectangle which has a certain area. It's the width of the rectangle times the height of the rectangle. The height of the rectangle is just however high f is at that moment. And the width of the rectangle is just
delta x.
And so, this is the kind of proof that Leibniz would have done back before there were like limits and all that distracting crap. What is the change in b? The change in the b function for a tiny change in x is just the area of this extra tiny little infinitely small rectangle that you added. And the area of that little tiny small infinite rectangle that you added is f of x times delta x
over delta x.
Whoa.
It's f of x. Whoa.
Very question. What is the derivative of b? It says, for a tiny change in x, how much change in b do we get? Well, the change in b is just the area of the little tiny rectangle added. And for a tiny change in x, the change in the area is just whatever the height of the function is. That is basically a proof of the fundamental theorem of calculus, which makes it extremely obviously true. And I want you to carry that with you, like in your heart. But this is also a proof appropriate for like the 17th century. Do you want to see the serious proof, quote unquote, with algebra?
Yes.
Okay, the serious proof, quote unquote, with algebra, as Sam keeps saying, is really no different. It just uses all the like definitions of all the things that we have already. So let's go.
Yeah.
Woo! Define a function to be. Wait, let's see how do I want to do this. Should probably like at least have a peek at my notes and start like written by a very.
Are you talented and smart person at your party?
Exactly. Good. I don't even really like need to. Keep it going, guys.
It's all going on YouTube.
Yeah. Good. So wait, staying on task. We want to take the derivative of the integral. Wait, no, stop talking. Good.
He just
Our theorem is that the derivative with respect to x of the integral from a to x of f is f of x. Okay, so I think it is convenient for us to temporarily name this thing on the inside to be a function. That's not going to help everyone, but that will help some people. So let's just let this accumulator function, let's just call it g temporarily. So let g of x be the integral from a to x of f. Cool? Say cool.
Cool.
What's up?
What happens if x is less than a?
Don't worry about that right now. It all works out, but yeah. Oh, by the way, why do I keep just writing little a? Someone say something about that. Why is like where I'm starting sort of so irrelevant that I'm not even giving you a number here?
Because like the definition already incorporates like the fact that it's the value of the function and like the value of the function.
Wait, hold on. Let me just answer my own question. When we ask for the rate at which this function is changing, we're asking what's happening to the b function like at that moment. So we're not interested in the actual value of the b function. This is like deep and important. Christine Chen? We're not asking for the value of the b function. We're just asking for the rate at which the function is changing. So does everyone see that it doesn't matter whether I just started integrating 2 minutes ago or whether I've been integrating for 200 years? If I've been integrating starting just 2 minutes ago, my b function might be huge. And if I just, other way around, if I just started doing it 2 minutes ago, my b function might be small. If I've been integrating for 200 years, my b function might be huge. But how big b is not the question under discussion. The question under discussion is what is the rate at which the b function is changing. So this is kind of like a what are you doing now question. Does everyone, did that explanation work?
Yeah.
Okay, I will try it again when it comes up, which it will. Okay, so wait, staying all together and focused, but also with passion. Let g be this inside thing. And so in other words, what I'm trying to find is the derivative of g. Agree? That's the whole problem. Well, if we were now going to prove this, like, rigorously and stuff, then there's only one possible thing to do if we are trying to prove that the derivative of g is f.
Right, definition.
That is, use the definition of the derivative. What is the definition of the derivative of g? It's the limit, as h approaches 0, of g of x plus h minus g of x all over h. Okay, great. What now? Okay, they've caught on. If they say do it, it sounds like they're saying something deep. But yes, we can just do it. By do it, maybe he means that this writing this thing as g was just kind of a temporary move to sort of make it cognitively easier to process. In fact, like what we are really doing is we're taking the limit as h approaches 0 of, well, what is g of x plus h?
The integral from a to x plus h of the f of t dt.
Mm-hmm. Yup, Adam and Valentina are simply just applying the definition of g, and then minus the integral from a to x. All over h. And like, if you think about this for even a second, what is that numerator?
The change in the area.
It's just that tiny little blue rectangle I just drew, right?
Yeah.
But, okay, so, I mean, I wasn't kidding, Sam, when I said it's just the formal proof is just the informal proof, just formalized, right? Because look, here we are at x, and we have some function here. And now, what are we doing? We're letting x be a tiny bit bigger. And so this new point I'm calling x plus h. And we got something that looks like that, right? And so intuitively speaking, the integral from a to x plus h is just all of it. And the integral from a to x is just the integral up to x. And so those are being subtracted. And so what do you think that numerator like sort of just must be?
Like x to h.
Yeah, using like the picture, it certainly just is the integral from x to x plus h, yeah? Okay, but since this is like a big kid proof, we shouldn't just use the picture. We should use integral properties. Fernand says we will now use integral properties, which says that you can break up the integral from a to x plus h into the integral from a to x of f of t dt plus the integral from x to x plus h.
Whoa, and then like they cancel. And then they just they go shoot.
That's pretty crazy.
Cool, 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 cool.
Yeah.
Okay, and so what falls out of that numerator is exactly what the picture suggests. It's like the limit as h approaches 0 of,
Don't you have
well,
to make the x plus h like just an h?
what?
Isn't that x plus h supposed to be just h?
No.
Oh wait, because like function.
Integral from x to x plus h of f of t of dt. And then there's just this kind of
wait,
1 over h just like chilling on the outside, yeah?
Yeah.
Okay, well, in other words, where are we now? We're exactly where we were on the backboard when we were doing it 17th century style, but now we just have like, throwing around the word like limit and stuff, right? It's just the area of this, or it's the area under this curve. It's no longer a rectangle. It's the area under this curve, like as h goes to 0, but then like also divided by h. Okay, now, does this sort of thing in brackets remind anyone of anything
Like
from
the
before?
average, like velocity.
Yeah,
Mean value.
yeah, this is just the average value. This thing inside the brackets is just the average value of f on the interval x plus h. That's what the average value is. You take the integral from x to x plus h and you divide by the width of that interval. And so what we now have is a situation, do you want me to redraw this picture bigger or just leave it? Okay, so what we now have is this, and is someone like taking care of the camera and stuff, or is everyone zoning out? Someone please like make sure we're staying in frame. What we now have is an understanding that this thing inside the brackets is the average value of this function on this interval. And what we, right, the average value. And now we invoke
The mean value theorem.
the mean value theorem for integrals to say that there is a certain point, c, on the interval x plus h, where the function has this average value. So, by the mean value theorem for integrals, there exists a point c on the interval x plus h such that f of c is the average value. And the average value is 1 over h times the integral from x to x plus h of f of t dt. And so, okay, this is getting kind of disorganized, but, and so, so I can do one final thing, which is to rewrite this as the limit as h goes to 0 of
F of the
F of c times.
just f of t, right? This is what we just did here, right? We have what the mean value theorem for integrals does is it formalizes this final step. It says that on this little tiny interval x plus h, which is not actually a rectangle, right, but is curvy, there exists a special representative point c, which like captures that function on that interval, in that the value of f at c is equal to, is a height for which the area of that rectangle is the same as the area under that curve. And so, like, this thing inside the brackets just is f of c, or rather, there is some c for which the thing inside the brackets is f of c. And now, what is this?
It's just like the 1 point.
That
But the thing is, as h goes towards 0, f of c is the only value that's possible.
This goes to f. Since, as h goes to 0, c has been defined to be somewhere between x and x plus h. Boom. That's it. Right? C goes to x because c is this point that we've proven must exist in between x and x plus h. As h goes to 0, c is squeezed between x and x plus h, and so c goes to x, and so this is just f. Woo! It is beautiful. Now, I've been trying to calm you down for the last 20 minutes. Let's do the opposite. Noisemakers. Go, Rajiv, give one to everyone. 2 minutes of just chaotic, like blowing. Actually, everyone just come, just like grab one really quick. Yeah. Would anyone like something that doesn't make any noise?
Yes.
I mean, everyone around you is getting, I think maybe, Dome, you get 10 total blows. That was 2.
That one.
Who's counting?
Is this recording? Is this recording? It better be recording.
My rules are, what are all those big words like capricious and all those other things? Like, there's not going to be any logic to it. I'm just going to grip the thing out of your mouth and throw it in the garbage. With no warning. So wait, what you need to do is anticipate. Wait, put the thing down. Down.
I was trying to play
down. Adam, down. Everyone sit down. Place your noisemaker, Bracklin. Down. Down. Good. You should raise that board.
Down.
You're good. Okay. Good. No. Bad boy. Down. 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 On your desk. It's like what you do when you get pulled over by a police. Hands on the steering wheel. Okay, good.
Wait, don't you not want their hands on the steering wheel so they can't like go away?
Okay, wait, no. Just do that thing where you think and then say nothing. Okay. Good. Woo! Guys, the fundamental theorem of calculus. Amazing. It says that the derivative of an integral is the function. What if I told you that is only half of the fundamental theorem of calculus?
I would not be that surprised.
In fact, it is, like, in my opinion, it is the deep half, but it is not even like the useful half. The useful half, the other half, I'm going to tell you right now. Are you ready?
Yes.
So this is also the FTC. I believe our textbook calls it FTC 1, but other textbooks call it FTC 2. There's no coherent name. Okay, here's the idea. First, I will give you the big idea. Let big F be a position function. Great. Well, as we know, because we set it up this way, worst board erasing job ever, the derivative of this function big F is some function little f, and we have previously defined the velocity to just be the derivative of big F, yeah? So this will be the velocity. This is not a proof or anything, this is just, we're just kind of building up to, again, make this kind of obvious. Well, great. If little f is the derivative of big F, then, and now I bring in the other major thread of this course so far, then we could also say that big F is an antiderivative of little f. Agreed? Sam? Whew. Okay. Well, imagine you sort of go to make a picture of this or whatever, and I guess this is a picture of I guess this is a picture of like of little f. And so what we have is some kind of thing that looks like this. And well, if I have this big F position function and I have this little f velocity function, then of course, as we already know, when I take the integral from a to b of this little of this function little f, then what do I get? Well, what I get is like the change in position. Okay. So what I get is like the change in, I get the displacement, right? The change in position. But if big F is that, then it's just the change in position, and the change in position is just the difference between the position at the end and the position at the beginning. Okay. This is just stating a bunch of things that you have 100% already processed, I think. Yes. But now I just bring your attention to the fact that this big F function is like an antiderivative of this little f function. And the second half of the fundamental theorem of calculus says that this is not a coincidence, and that in fact this always happens. This is true not just for the position function that you sort of differentiated from, but it's true for any position function. So like theorem, if you are taking an integral for some kind of reason, you may take the integral as follows. Find yourself an antiderivative, if one is available, and simply evaluate that antiderivative at the upper limit of integration and the lower limit of integration and take their difference. Where big F is any antiderivative of little f. Any. Whoa. Whoa. Okay, proof. This would have been nice, yeah. It will be nice in the future. Proof. The proof uses what I call the fundamental theorem of calculus part that we've already proven, and just kind of makes it all work. So here we go. What I want to do is I'm given some integral, and I want to show that this integral can in fact be just evaluated using some kind of antiderivative. Okay, so let's go. Define some function g, some new function g, to be the integral from a to x of f of t dt. Okay, that's like basically define an accumulator function which evaluates this up to some generic form. All right, well, what is the derivative of g? By the fundamental theorem of calculus that we already have proved and talked out and loved, the derivative of g is just f. Agreed? Okay, well, if the derivative of g is just f, so great. Okay, so now introduce some arbitrary other antiderivative. Let big F be an antiderivative of little f. Some antiderivative. Okay, great. Well, by the very definition of antiderivative, what we know is that the derivative of big F is little f. I'm just going to pause for a second. So I start with this function little f, and I want to know what the integral from a to b is of that little f function. I first turn it into an integral function and just observe that the derivative of g is f. But if I have some other antiderivative, then its derivative is also f. Well, now, and we've reviewed this a couple times, so this should be relatively close to the top of your brain, what can I say about these two different functions, g and big F, if both of them have derivative little f?
They differ by a constant.
They differ by a constant, right? Since, So since big F and G both have derivative little f, or both have the same derivative, they differ by a constant. They differ by a constant. In other words, big F just looks like G as some kind of constant. Okay, all of this was just setup. I started with some function, little f, that I wanted to take the integral from a to b. I defined this function g. I applied the fundamental theorem of calculus to say that the derivative of g is little f. I introduced an arbitrary antiderivative, and if it's an antiderivative, then basically it must be some sort of g-type thing, plus a constant, because that's how antidifferentiation works. Okay, so now we start the proof. And the proof's just like, basically just like 2 lines, right? Take the integral from a to b of f. What is it? Well, it can be thought of as just, actually I guess this isn't the way to do it. Maybe to go from right to left is the better way. So just take f of b, well, okay, I guess it doesn't matter. So take f of b minus f of a. What is f of b minus f of a? Starting on the right-hand side of the theorem I'm trying to prove.
G of B plus C minus
F and g just differ by a constant. So this is just g of b plus c minus g of a plus c. But then the c's just cancel, right? Is the camera keeping up? It seems like it's not.
You got it.
Yeah. And so this is just g of b minus g of a. Okay, but what is g of b?
The accumulator of the integral from a to b of f of t dt.
Yeah. Well.
Minus 0. Oh my gosh, and it's just like 0, man.
And we are just done. Whoa.
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 What this says, and this is like almost kind of just like shocking.
It's on the board now.
Yeah, wait, what this says is you have some integral you want to do. Let's say, what was the problem on this quiz that I gave you? Does anyone like know it by heart? The problem on the integration quiz that this class did that I had back on Monday?
2x squared minus x plus 3.
2x squared minus x plus 3. That's from 1 to 5 or 1 to 4? 2 to 5 or 1 to 5? Okay, good. From 1 to 5. Alright, so I posed this. This was like, what's up? Yeah, of course I do. Yup. This was a problem that you guys did. Anyway, this was a problem that you guys had in a quiz, and I made you just tough it out and suck it up and do the whole thing out. And what did you do? This incredibly convoluted process, which seemed at the moment to be totally necessary. What else would you possibly do? You go and you go to 1, and you go to 5, and you go and you take the value, and oh my god, I want to put the area into this curve. This is so hard. I need to split this integral up into subintervals. Subintervals all have equal width. I'm going to construct rectangles. I'm going to come up with these complicated theories to figure out the forms and the patterns of all the rectangles. I add it all up. I apply all of these previously proved things about sums of squares and sums of cubes and all this kind of stuff, and then I take the limit as n approaches infinity, and then I get a number, which was, does anyone remember the number?
248 over 3. Yeah.
248 over 3. Alright. Armed with the fundamental theorem of calculus, we now know that this is not necessary. As long as one has access to an antiderivative of this function. Do you know an antiderivative of 2x squared minus x plus 3?
Yeah.
Please name one. Name a function whose derivative is 2x squared minus x plus 3. I think there's like it's gotta be like 2/3, right? Is that what you said? 2/3 x cubed.
Minus 1 half.
Plus 3.
Wait, this is B, 3x plus C.
Well, plus 0.
Okay. So wait, shh, good. So what we have just done, is to pull sort of out of thin air using anti-differentiation skills a function whose derivative is 2x squared minus x plus 3. Yeah. The big picture of why this all makes total sense is that the sort of goal that inspired finding the area under the curve to begin with is that you're trying to find the velocity versus you want to find the area under a velocity for the time curve to find the change in position. And so the thing that some of you might have already thought of like 2 weeks ago is, well, dude, if this is a velocity curve, then let me just like construct the corresponding position curve. That is kind of what's going on here, right? I'm sort of just saying, taking this velocity curve, well, the thing is that there are an infinite number of different position curves that have this as their velocity. They all differ by a constant. Is everyone feeling this?
Yeah.
This is like the whole course right here. Okay, so this is not necessarily the position curve, but it's like a position curve or something like that, which might be kind of off or something. But it doesn't matter, because all I care about is the change in the position from 1 to 5. So if all I care about is the change in the position from 1 to 5, then I can just find the position at time 5 and subtract the position at time 1, and that will give me the change in position. And if my position function wasn't the right one, because I'm actually off by 300 miles, it doesn't matter because I'm going to be off by 300 miles on both of them, and all I wanted was the change in position in the first place. And so, okay, so that's like the thinking behind it. And the fundamental theorem of calculus part 2 that we just proved says that when it comes to actually doing this, man, it's like the easiest thing in the whole world. The answer to this problem is, it's just big F of 5 minus big F of 1. It is totally intuitive, bordering on almost just obviously true. That what now comes down to is if you need to do an integral, and we often do need to do integrals, you can just do it by finding an antiderivative of the integrand and evaluating the antiderivative at the various places. Whoa. And the notation for this is that when people are pressed with this integral, what they often do is they in sort of brackets or something, they go like this, and then they say, to be evaluated at 5 and 1. And when you evaluate this at 5 and 1, you get, well, should we just do it right now?
Yeah,
Let's
sure.
just do it, right? You get sort of like 2/3 times 5 cubed, right? Okay, but okay, minus sort of like 1/2 times 25 plus 3 times 5, and then all of that like minus
Well, you get like 2/3.
Then you get
2/3 times like 1 minus 1/2 times 1, and then just like plus 3 times 1. Okay, so it's still a little bit of like arithmetic to do. I think the smoothest way to actually